special case for hemispherical relativity plus QED loops as the underlying atomic, subatomic physical model. So when is a three-way intersection at 90 degrees not orthogonal? Orthogonal is a very mathematical term that means that you can change and rotate and everything works very cleanly. Well, the answer to that is hemispherical or spherical or similar coordinate systems. So technically at that point on the surface, there are three directions to go: outward from the paper, to the right, or to the left. And those are at 90 degrees. But strangely enough, those are not going to give you orthogonal because these two directions curve on that sphere surface. So this meets at 90 degrees, but is not orthogonal within the meanings of the equations that we have to build. Now, a physicist might understand these words and what that does. You see, a change in the radial direction causes a proportional change of the inclination. And in physics, we use the term covariant for that sort of a math relationship. But the reverse, a change in the inclination, does not change the radial distance scale, because you're still along the surface. So that direction is invariant. And strangely enough, that means if you go one direction, you get one relationship, and if you go the other direction, you get a different relationship. And that's the ability of a function to go A to B and is the same as B is commutative, or abelian in the fancy physics terms, and thereby this is non-abelian. It does not reverse. Similarly, there are other things that happen. And in total, you get basically a specific relativity model. I'm not talking about general relativity of Einstein. That is the global one. I'm going to talk about the specific hemispherical relativity and how that is the specific case for the subatomic procedures. And that actually will give us all the answers that we need without having to do all the complexities of the space-time in Einstein's things. And that leads to another thing, but if you change the inclination angle, the change to the latitude is not at a consistent ratio. It sort of depends upon the angle that you're at and the initial state. And thereby you get these things called initial loops, both in general relativity and in quantum electrodynamics. And in the final way, hemispheres behave as a reflection across the equator. And so that the Pauli pair at 180 degrees, if I move right, the other one moves left. They're sort of locked in with a nucleus as a fulcrum. And so they are not covariant, they are contravariant. Again, these are specific words, and we're going to go through and show how the hemisphere relativity does this. And you can apply specific formulas easily to understand this without having to go into the abstract 10 equations of the full general relativity of Einstein. So these things are important. Now, what is the frame of reference that we're talking about? It's the hemispherical frame of reference. And that's what are electron subshells. They are longitudinal rings of electrons. 1 at the poles, with a matching one down here. 3, 5, 7. And then in certain odd count exceptions, you'll get this equatorial of 3. And for each set in this side, the green has a green 3 down here, a 5, a 5, you get hemispheres. And so that gets 2 times the odd numbers for the subshells. Except, of course, the equator, where there doesn't have to be 2. And the same way on the shells, the sum of odds equals the squares. And so 2 hemispheres times the tightest configuration, the circle, squared, okay? That's how you get 1, 4, 9, and 16, which become the periodic table 2, 8, 18, and 32. Now, the second major object of understanding these subshells is that longitudinal ring here is the electrons in that set all coming out. And they have four forces that keep them in place. Two in the radial direction, outward, and two which are effectively just in this axial directions towards the axis of the nucleus. So the proton-electron electrostatic force, we all know about, that goes towards here. Now we also know the Bohr has an extra 1 over r opposite force, and that's a repulsion. I've related that in my earlier papers to the strong nuclear force. Okay, it is opposite, but its scale is extra 1 over r. So there's a point at which those two balance, that being the Bohr radius for the simplest 1 proton, 1 electron interaction, which is a hydrogen atom. So the Bohr hydrogen atom, A sub 0. Now, the weak force is axial and is based upon the strong nuclear. They're both nuclear with that extra 1 over r, but this has a sine cosine in magnitude and is pointing towards the axis. But the thing is, if you get 3 or 4 or 5 or 7 other electrons with that same rule, they effectively all end up in this 2D plane, and they all sit at the same distances, and the repulsions between them, the electron-electron radial electrostatic repulsion, is in the opposite direction. And so you get equilibrium this way and equilibrium this way, and you create what Bose in 1924 used as his proof of statistical mechanics, because he called it that the causation is a cylinder surface, and it has an extra 2 times in his things that he says must be from polarity. All right, so there's basically 2 postulates. One is the fundamental static forces interact. The main one, radial electric versus radial nucleostatics, create shells. The electrons do not fall into the nucleus, they stay in that. The second one is these behaviors are hemispherical by the model here. And that is, there's here, but there's also a second set over here. Now that leads us to the quantum numbers. The quantum numbers are just the hemispherical coordinate system. The first quantum number is the layer. It's the radius, and I apply the pound sign just so that we know this is not a mechanical, this is the count of numbers. Then there's the inclination, and I use the word inclination versus longitude because it's from the poles. That's the angle from the poles. A longitude is an angle from the equator, which we'll know from the maps and the globes that we all use. And then the latitudes is the third quantum terms, and we use theta for inclination, and we use phi for the latitude. And these are counts. So you're taking the actual 90 degrees and then you're dividing it up by these, which I'll show later. And the fourth one is the hemisphere. And the hemispheres, of course, become a +1/2 or a -1/2, because for many calculations, we can only use half the energy. You're in a hemisphere. So, but the thing is, as I showed in that first diagram, these are not orthogonal. And the equations that you use today don't do that. They're not orthogonal. But then all the things you do in quantum mechanics and in general relativity is the ways to do error correction. Quantum theory provides error correction for the abstract algorithms that are originally meant to be orthogonal. That's your standard X, Y, Z. So if you turn something or you move it, it goes in its particular way. All right. So, as I said, on the surface, there's a radial direction and there's X and Y. The thing is, we actually know this all the time because that radial direction is the energy to go from this position to infinity. That's called the ionization energy or release energy or various measures that we do. And so we're actually, for hundreds of years, have been measuring this, and this is the most common thing that we get in statistical mechanics. The real question is what happens in these other directions. Now, this is spherical coordinates, so if you go this way and that way, the curvature of that is the same. However, I'm presenting that we're in a hemispherical coordinate system so that the curvature here goes all the way around, but the curvature in the third quantum number, the latitude, is along this line, which could be the whole thing, but it could be smaller and smaller and even be a tiny one, depending on what this inclination angle is. And so these are three very different when you use the hemispherical. And at the hemispherical, because that line of electrons, the electron subshell, is at that thing, it becomes very important. And this is how subatomic physics and electron subshells work. Okay, so my model already has supporting evidence. Rabi already determined that the deuterium, that's the helium version, hydrogen version with an extra neutron, has a non-zero quadrupole moment. And that means that it's prolate ellipsoid. That means it's 50% longer than it is wide, because you've got the proton and the neutron, and they form an axis, a nucleostatic axis. So that evidence is about what I call my nucleostatic axis. They have evidence for it, and they say it applies, and it's in fact of great importance, but then they go ahead and they use an orthogonal XYZ equation, basically doing that. Secondly, Ange-Bohr, the son of Max Bohr, Modelson and Ringward got the Nobel Prize for the completion of this work. And it's very interesting and very good, and basically proves that they are oblong, somehow hemispherical nucleus sections. Now, my thing is that electrons are also the same. And we all already know this. You see, in basic chemistry, the strict Aufbau rule says that you start building these things and you go one, and you build from shell 1 to 3. And this is, remember, in 2 hemispheres, this is just 1. So you double all these. There's 2, 6, 10, and 14 in each subshell. But there's a matching set up in the top. Okay? Now, the thing is that the energy levels, these fill with, say, shell 6, but you're told the rules are that you have to, that the count for subshell D is n-1. So everybody's always asked me, why did we have shell 5, and then we go to shell 4D, or shell 6, and shell 6, 5D, and then 4F, okay? Well, the thing is that the energy, that distance from here to infinity, is n-1. That is prolate. That is a hemispherical scrunched structure, okay? Now, why does that happen? Because these line up, and along the axis, they're all pulled towards the axis, so these line up in a straight line. But because you get 2 layers interlaced, because there's 2 hemispheres, you can take 3 points, and if you rotate them a half a phase, they fit slightly tighter. So we get the periodic table of 2, 8, 8, 18, 18, 32, 32. So that path is a little diagonal, a little bit shorter than the path down there. So that your electron shell here is effectively energy as if closer, which we've all seen and we've all learned, okay, but we haven't learned it with the 3D model. So what happens? Well, you see, if you're moving along this shell or you change any of the orientations, the expectation of an XYZ is that that line's going forever in that direction. But really, it's going along this loop. And you'll see 2 pi, which is the circumference of the circle, and you'll see that in various places like reduced Planck, and in places like the anomalous moment of a Schwinger. He got a Nobel Prize for that. All right? So what happens? You see, in this, I want to apply, say, Pythagorean's theorem, which the distance is the square root of x squared plus y squared plus z squared. This is orthogonal systems. But think about that globe. If I move north, move the same distance south, move south again, and then move back to the east, I go what you would think would be a square, but there's this gap because the distance around this longitude, the curvature of the latitude, is different than the curvature here, so that space is warped in the ways that you see in science fiction from things, people extending Einstein to places it's not supposed to go. That gap is the difference because you're not working on an XYZ based system. So let's talk about Einstein for a second, okay? Einstein, in his general theory of relativism, says physical laws are good in their simplest form, and the same laws hold true in relationship to any other coordinates k prime, a translated one, moving in a uniform translation relative to that. Now, I can test that statement because he's assuming it's XYZ. That doesn't apply for hemispherical situations. So the law of transformation is this in his book, where basically he says, if I put it down here, it is, covariant. Remember covariant from the very beginning of my paper? He says, oh, by the way, if you do that, I'm going to get covariant, okay? And sometimes I'm going to get contravariant. But if I have a contravariant, then I'm going to put the subscript on the top. So covariant goes down here, contravariant goes up here. And you sum all these things up, and basically you get this transformation A prime, which was the original system, with all these partial derivatives. Now, we don't want to do that math because since I know the axis, I can already calculate it. I don't have to do the warping of time and space because I can just choose which one of the radial, inclination, theta, and the hemisphere, but obviously the hemisphere never becomes, it becomes invariant because you're either one or the other, not really that difficult, okay? But the other ones are important to understand. So in that plane, at the axial plane, you get the radial inward and you get repulsions. But since they're balanced in distance, these vectors add, that's what the little hash thing is. And so you get this black arrow matching the red, and there's an equilibrium. However, guess what happens? You've got other things, okay? I will get you, so that means that these other electrons, even within this ring, are bumping into each other. That it is not a continuous ring, but it is quantitized. So it is this level. This is the start of statistical mechanics and quantum theory. It's not an individual electron, but it's only in electron subshell sets where you get what could be a ring, but you get individual ones, so they're bumping you into each other, and that adds the extra math to get you the statistical methods of statistical mechanics, okay? Now, you can see this already. Go look in your textbook at the electron distributions. Look at them. They're rings at a particular latitude, okay? Those are all those two cylinders. And they're quantized at this level, so you can't get an exact because you don't know exactly how they're bouncing into each other, but you can get a pretty good sense by the equilibrium that I described. Now, as you know, there's two exceptions to that. Obviously, the two poles, there's no bouncing around, so you lose that one set of statistical mechanics, and you end up with the older pre-Gaussian type subshells. And the ones that are here are Slater type subshells. And that becomes a Slater differential. And this becomes just a two-dimensional radial because there's no extra axial in this part. Similarly with the equatorial is you have this, but you don't have two of them matching. So you lose 1 degree. So it's sort of intermediate. And maybe I'll write a paper on that equatorial more specific because it's a strange version of the Slaters. Now, my paper abstract of APS showed that there's supposed to be 2 at that, but here we've got an extra one. I agree and present that the equatorial should be separately. It's a transitional equatorial subshell. It does not apply in full subshells, but by having 3 in it, it handles all those odd count electron configuration exceptions. All right, well, back to relativity. So this abelian and non-abelian, that's basically A function B is the same as B function A. Okay, it's a math commute, okay? And that's fine. Let's start with the easy one, in the latitude. If I change the latitude, say from over here to over there, the radial distance does not change, and the inclination angle does not change. It is invariant. But if I change the radial difference, if I go from the original one out to this bigger sphere, the distance from here on the inclination changes. It grows, and the distance around this, all these latitudes changes to a bigger ring. Now, this ring here is the full circumference, and this ring is the circumference times the sine of that theta. And that becomes interesting when you change the longitude. You see, you change the longitude and the latitude changes, but it's not exactly the same. You're making a distance, and that shape itself is a sine of that change in theta. Your original theta, your new theta divided by the original theta, but the sine theta divided by sine theta is the math change of the size of those two rings. If you change by 90 degrees, that one thing can come up here to 0, okay? And so this is a different type of, it's not a direct covariance, like here. If that grows, this one grows directly, and that one grows directly. This one has a sine function, a wave function, something with a theta in it, okay? So now we have the 3 basic rules. We'll get to how they work, okay? So if we're doing that, we're doing scaling. So whatever dimension I'm in, I've got the old distance minus the dual distance. That's the change in location. And in Pythagorean rules, it's all real simple. That's all that Pythagorean theorem. If I want to know the distance, that really is the x squared plus y squared plus z squared square root. But that's not so here. In this radial difference, I said you would do a change here and nothing happens to the other 2. This is the invariant rule. And so this matrix brings you no changes. It is invariant. And this is how you describe it in presenting the math. There's the picture, and there's the math. You change this one, nothing happens. That's what typically happens. If I move along the x direction, nothing happens to the y. If I move along the y direction, nothing happens unless there's a specific interaction that does something, obviously. So let's now go look at the other one, okay? If I change the radial one, in this case, the new one becomes that same covariant, this same ratio of the change in radial, then it gets applied to the theta and gets applied to the phi, the latitude. And so this is a pure covariant reference. So any transition from where the base is a dimension that is radial, all actions must be applied to the other ones. It is not orthogonal. It does not follow those orthogonal rules. And finally, the strange one that I talked about, if you change the theta angle, nothing happens. You're still along the surface, so nothing happens. It is invariant towards the radial direction. But, oh, that's only me. That's a divided sign. The change of the radius section is from the original theta to that. That's 2 very interesting things. So here it is in the same things. Whenever we chose the green one, it has different effects by which way it goes. So how are we doing it today? How is Einstein doing it? And how should we do this? You see, if we start from the radial direction, which is the one that most physics does, we get covariant applied to the other two. We typically measure this radial distance that I explained before is the ionization energy, all the things we measure in physics. But then once we move this, guess what? That means that we also move this, so we get this applied, and then we get a secondary effect applying that one. And so you have to do this two-step analysis, which is one of the things that actually was in the general method, but in this way, it is very specific. Now, the funny thing is that if I do a change in the theta direction, this is invariant and this is invariant, so that invariant doesn't change that one, which means it doesn't change that one. So if I do an operation on the theta direction that is between the electrons in statistical mechanics, it is invariant. You never see general relativity applied. Now, these two directions are different. This function going r to theta is different than theta to phi, okay? Now, I introduced that middle section here. This one, you've got a theta 0. And that theta 0 is not the same. And so you can't just say, oh, it's 50% or it's this times 20%. You actually have to do the calculation of the theta 0, the sine theta at time 0. And that becomes a frame of reference challenge. Because if you don't do that, if you don't change the theta, you're going to get a different answer. So that vector times the subshell, okay, becomes the theta of 0. And then doing this at time 1, but guess what? Now when I do that ratio, I did it correctly, no, sorry. These two get applied, but guess what? I've got a subshell vector S in both cases. You see, the secret here is that this angle is the cross product of that with subshell S. Subshell S is always the nucleostatic axis, okay? So now I can eliminate, and because I can eliminate, I can really get down to that. Now, what you're taught in the textbook is a procedure called Rodriguez, which is the orthogonal translation taught. That would give you this translation, and that works if you're an X, Y, Z. However, as you know from the section above, that translation is not orthogonal. That translation is based upon where you are in that three-part matrix. And I'm doing, say, one from the rotation on theta. And that would give me this ratio. And those are items that you can calculate. Okay? Now, why do you need this? Well, you see, if you have particle and particle 2, and this has an axis, everything is pointing to that. In regular statistical mechanics, if you don't know that axis, it calculates by I. And the math is, the position is E to the exponent I R, okay? And that's the main part of what's called the Schrodinger equation. So we get distance scale distortions, and we get initial state missing requirements. And that's what is QED. So general relativity is a radial change in distance, changes the other two, covariant. The wave function, though, is any change to the longitude or the inclination dimension is not linear, but creates a wave function based upon that. These matrices are non-abelian. That means they will not be diagonally symmetric. Okay? And then whenever you're doing this, you end up with these initial states based upon a sine wave, okay, a wave function, but you have to have the original state, which is how we're going to basically get to QED loops. And the same thing is that when they're doing it today, they're going to teach you SO3, which is basically the orthogonal translation groups, or the R3. You'll see this in textbooks. Those are the orthogonal methods. You must update them with hemispherical relativity because they assume that no translation and that Rodriguez method. And that Rodriguez method needs to get replaced. And of course, finally, to do this, you must understand the scaling factor, which is Bohr over the electron equilibrium versus edge scaling factor. You have to understand polarity from Bose's 1924, two hemispheres. And you have to understand the cylinder surface being longitudinal rings of odd count electrons becoming the balanced set that becomes statistical mechanics. Now, in fact, you actually see this. This is a QED calculation of the fine structure constant. The fine structure constant is that ratio, but to the -1/2. It's a special case of this equilibrium. But to get the answer, they basically apply these different versions of the particle sets that are intertons. The quantization has to be done these 14 ways, or in another case, another piece of paper, 32 different ways, and they get the exact calculation. But in reality, I say that what they're doing is they're looking at from this target electron, seeing the 2, okay? Okay. Or from this target electron, looking in the other hemisphere at the 3. Yeah, sort of looks maybe like that, or like that, okay? And so those things that they've done in these abstract forms is really, again, translated from hemispherical systems. All right, so how do you calculate this? You see, if you've got that subshell-s on the nucleostatic axis, only 1/2 of it is here. And this, of course, is a movement of 90 degrees in the hemisphere from pole to equator. So what we're doing then is another thing, and that is you end up with this extra 1/2. And that's called quantum spin, of how many units are there versus the inner layer of spin. And you'll see these spin units of 1/2, 3 halves, 5 halves, 7 halves, but without a physical model. So you can see that if you're building a 1, 3, 5, you only get 1/2 on this one, a 1 and a 1. And that means that you get a total spin factor, physics spin, of 2.5 for the 90 degrees. Now, that 90 degrees gets a little overlapped because this one can bounce a little bit over because they're interlaced again. That would be the without the half phase interlacing. All right, so what are the rules that we can do? Avoid the XY framework when you're working on subatomic things. Remember that inside 10 times the Bohr radius, the nucleostatic axis becomes dominant. It's no longer unused. You can use the closed container ideal gas law. You can use gravity when you're talking about things at that distance. But once they get that close, that number is material to your calculations, okay? Orientation should be always from the nucleus frame of reference. If you're trying to do that axis and you're off of it, you're going to get some strange relationships, okay? And those application of these becomes quantum numbers in the hemispherical coordinate system. The radial direction is 0, 0, 0, that's the nucleus, and the poles are at 0, 1, 0, plus 1/2 or minus 1/2 for the cells. And if you set up those coordinates, you can do those calculations that I showed. Okay, any evaluation needs to put inclination ahead of latitude, okay, because that introduces that initial state factor. If so, you're going to have to do loop after loop after loop. And this is how, by using my system, if we do the reverse of that and we analyze the electron subshells as a set, not caring which latitude they are, we eliminate the QED method and the computational load diminishes exponentially. Okay, so this order should be latitude, then inclination, longitude. That's the electron subshells. You are not evaluating electrons alone in my version of computational chemistry. And radial is done finally, and that then would, of course, the radial changes would then collinearly just change all of those without changing their signs or their thank yous. We can eliminate all these things. You also have to remember the Pauli pairs are 180 degrees, and that the power and the distance to do that. And because it's missing the nucleostatic, you get 2 cubed times 2 cubed minus 1 cubed. And so that becomes 8/7, which becomes your electron position in a Pauli pair, which means everything except for a hydrogen atom, is the average distance. And rotations introduce these theta errors and the initial methods. So when you learn QED and those, you'll be able to identify where you need to apply it and in which ways, which things are contravariant, which things are covariant, and which ones are invariant. Now, what is that curvature? The curvature that I talked about, we find all over in statistics. It's the equilibrium versus edge, A sub O over R sub E. That is the ratio. That is the curvature. And the N, of course, depends on whether you're in an acceleration or a force or a density function, or if you're in that, or if you're doing comparisons of them, you get some actually interfaces. And so the common strength is H hat C at AO. Planck is at a particular distance. The strength of the system, of the interaction, changes based upon distance. Depending on which type you're talking about, is whether that's a squared, a cubed, a fourth, or some relationship ends. So that there's a special name for that that's called the fine structure constant, but that is just the root, the minus 2 1/2 root of that. And then the second thing you have to remember is that mass is two forces together, two fields. It's the 1/distance cubed and the 1/distance to the fourth. Now, of course, until you get within a little bit of inside the molecule, it looks constant. But once that R becomes materially small, if this R is huge, if this is 10 times A sub O, this becomes almost 0. And we have the fixed math of what Newton understood. But if you have a distance that inside of AO, but larger than R sub E, this ratio becomes material and dominant. In fact, that's how you get the difference between a proton and a neutron. The proton is at the center of the observation. That's the method. The mass is always based upon the proton or the nucleon field, or the ether of that. And so you take that ratio at the 3/4, but you add the Pauli pair, because they're always coming in sets of balanced pairs at 180 degrees. And then you have to add that anomalous moment, because this is a point equation, and those two things actually have a physical distance, which slightly adjusts, and that's 0.0015. It's a very tiny number, but to get an exact answer, you get it. That is the ratio of electron to proton mass. But it's based upon position in the field of where they settle. And of course, that also gets you that same A sub O over R sub E with that anomalous moment, okay? And these ratios get you to gravity. And gravity and mass together basically is everything that we're talking about, okay? So finally, this exponent rule is potentials, forces and fields, or accelerations and such, for both the electrostatic and the nucleostatic, the extra 1/R. So you have all these. But then as you do transitions or comparisons of those, you end up with these pro rata functions, again, of that scaling factor, okay? And remember this one there, that's the one for mass, okay? And so as you do this, there are three fundamental forces. Planck's strength is at Bohr. There's an equilibrium versus edge scaling factor. And there is this field or ether acceleration physics stack that you then have to apply to the different fundamental forces. And now I've added, you have to have hemispherical relativity, because this is not an XYZ orthogonal system. Those two directions, you have to know which direction you're pointing and measuring, because that changes the calculations. And then you remember those longitudinal rings and the operating units. Statistical mechanics does not work on individual electrons, but only on electron subshells that are already settled into these longitudinal rings. And of course, I then go ahead and eliminate the things that are not this scaling contact, that are not Planck-at-Bohr, that are not these, and I get rid of these mixed variables and constants, like the gravitational constant, like mass, like charge, like Coulomb's constant, permittivity of space. And I effectively am starting to lift the veil of what is the physical model underlying the very complex thing that is modern physics. Obviously, I have a lot more to do, and we're only, say, 5 steps into things, but over the next years, that is my work.